Welcome to In 5 Minutes. The agenda of this clip is to understand EEPROM, EEPROM and flash memories. We'll be doing this not only in this clip but a few clips following this as well. In order to understand these memories, we need to understand the concept of floating gate and also Falun-Northam tunneling. We'll start understanding the concept of floating gate here first. So here the name itself suggests that there has to be a gate which has to be floating. Here is my normal MOS transistor with metal, oxide and semiconductor which I have drawn. The difference between this transistor and the transistor with a floating gate is I have added an additional gate. This is the poly gate which is kept floating. Floating means it is electrically isolated. It is not electrically connected to any other terminal or any other potential in your MOS transistor. If you're getting confused, I'll just show you what I have drawn. And the blue lines around this floating gate is nothing but your SiO2 layer or the silicon dioxide or your oxide layer. So this is nothing but the cross-sectional. This is my floating gate which is not connected to anything. This is my actual gate where I will be applying the gate voltage, so it becomes a control gate. And we know that there has to be an SiO2 layer, correct? So this is the SiO2 layer which is surrounding my floating gate. Now the whole idea is we are understanding floating gate because we want to understand a memory type which is EEPROM, which is electrically programmable read-only memory. You can program this memory electrically, and when I say electrically, you need to do something with your voltages in order to program this memory. Though it does not delete your memory because there is no erase word in the name of EEPROM. So it does not delete your memory or erase your memory electrically, but you can still erase it in a different way. When you can erase and program it both electrically, it will become electrically erasable, programmable read-only memory, which also we would see. This is a symbol for the floating gate. Let's understand how programming takes place in floating gate. I'm just erasing this because I want to show you something. Technically, we'll be able to do the programming of the transistor for EEPROM by storing some charge on the floating gate. Let's understand this. Basically, this is the curve of ID versus VGS when my MOS transistor is operating normally such that my VGS is greater than the threshold voltage. The erase operation will happen in case of EEPROM, and if my threshold voltage is increased to such a high value, then my programming mechanism will happen in EEPROM. We'll understand how you can get a threshold voltage of such a high value and what we are trying to do. Basically, if this is my NMOS transistor, which is a normal transistor, when VGS is greater than VTN, we know that the transistor is turned on. I want to make this threshold voltage so high such that when I apply a VDD also at the gate, still my transistor will not turn on because threshold voltage is higher than VDD. And in doing so, we'll be able to program our EEPROM. Let's see what and how. But the thing which we understood from this part was we need to increase our threshold voltage, and EEPROM revolves around storing the charge on the floating gate. Keep these 2 points in mind and we are set. So because we need to understand the threshold voltage, we need to understand the basics of threshold voltage. Here in the equation, I am not going to take into consideration this part, which is the positive charge at the interface, which needs to be overcome by the threshold voltage or should be counted in the equation. I am ignoring this term for the time being. QB, which is the depletion region charge density, is technically effectively negative for NMOS. So this minus of minus will become plus. So this is a positive term. Remember that. Now in a normal case, I have oxide capacitance as COX. In case of a poly gate, my COX would reduce by a factor of 2. Let's see how. This is my normal gate. This is my poly gate. Between my normal gate and my poly gate, there will be a capacitance. Let's call it as C-OX. Because there is an oxide which is present, right? You can see that. And between my poly gate and my actual substrate or my actual semiconductor, there will be another COX which is C-OX. So I can easily make out that CU-OX is connected in series with C-OX. And when they are connected in series, we know that this is what happens. So effectively, C-OX by 2 would be my new COX. If I put this COX back in this equation, as I said, this is a positive term. I know that if COX reduces, and there's a positive term, so my threshold voltage would increase. But this increase in the threshold voltage is very, very small, and that would be not of much use to us because we just discussed that we want to make the threshold voltage greater than VDD or a very high value threshold voltage in order to program my EEPROM. So for that, we will go back to the thing which we have already studied, how we can store the charge on the poly gate, or we will understand a concept called as hot electron effect, also known as channel hot electron injection or CHE. Now when we studied hot electron effect, we very well know that when my drain voltage increases, my VD used to increase I also had a gate voltage which was very high. Now when VD increased, or VDS increased to be more specific, we know that my E lateral increased because E lateral was VDS by L. Because my E lateral increased, my VD drift velocity increased because VD was mu into E lateral. Because my drift velocity increased, my kinetic energy increased because kinetic energy is rho half m velocity square. Because my kinetic energy increased, my electrons carried a lot of heat or moved with a very high energy. They were hot electrons, and these electrons moving with very high energy underwent a process called as impact ionization, which means that they pass the high energy electrons, pass their energy to the electrons, enough energy to the electrons so that they can move from valence band to conduction band, and therefore creating a hole in the valence band, or creating an absence of electron in a valence band. So an electron hole pair was generated. Hole, being a p-type, will move towards a p substrate in case of an NMOS and will lead to substrate current. However, the electrons might move towards the oxide if the gate voltage was very high. And we know that gate voltage was very high. I beg your pardon, that was a part of another electric field in MOSFET, which was given by VGS by TOX. So as VGS increased, we know that it used to attract the electrons towards itself. Some electrons will move there, but some electrons will get trapped in the oxide layer. This exact phenomena we will try to achieve in floating gate. The electrons which were trapped in the oxide, right? That is what we are trying to understand. Some electrons will move towards the gate, but some electrons might get trapped. So when the gate voltage is a very high value and the drain voltage is a very high value, we know that hot electron effect will take place, or channel hot electron injection will take place, which will lead to trapping of some electrons in this poly gate, which will leave behind a positive charge here. So the next time if I have to turn on the transistor, my transistor will require a higher threshold voltage to turn on. And this is exactly what we wanted, because we wanted to program our device in such a way that my threshold voltage is increased. So what we did in summary was we underwent a hot electron effect for my floating gate, where we increase the gate and the drain voltage. Now when we are increasing this gate and the drain voltage in order to trap some charge on my poly gate, and the reason why we are doing this is because we wanted to increase the threshold voltage. These voltages are becoming now the programming voltages. So we know that for programming, gate voltage should be very high, drain voltage should be very high. They should be in the order of 20 to 25 volts. Technically. Now we understood that from the analytical point of view, that when charge is present here, it will leave behind something now positive, and this needs to be overcome by your gate so that the threshold voltage increases. Let's understand the same mathematically as well. So VT, we had seen this term here in the previous slide. Now there's a new term, charge on the poly upon COX. This charge also, because there are electrons, is going to be negative, so negative will become positive. So here we know that Q poly is increasing, charge on the poly is increasing, COX is reducing, correct, COX by 2. So overall my threshold voltage will increase. And now I have increased my threshold voltage to such a value that it is greater than VDD. That means in an NMOS transistor, when a gate voltage, even VDD is applied, it will not turn on, but it will remain off. And this is exactly what I wanted. Electrically programmable ROM, correct? So I wanted to program my ROM electrically with the help of the voltages such that I can turn it on or turn it off the way I want. And I have programmed it in such a way that my threshold voltage is very high. So I can keep it off. Let's understand what I'm talking about. We have already studied ROM arrays, right? Where this is a pull-up, a pseudo circuit, correct? Just take one or two cases here. This was my output. This were your transistors arrays, correct? I've drawn here one part of that row, and I have replaced all that 4 transistors with a floating gate transistor. Some of them are already programmed high. How have we programmed? We had made their gate and drain very, very high, and we ensured that that charge was trapped onto the poly gate. And mind you, this charge stays there for long time, for a lot of years. The charge can stay there if you don't erase it. So this is programmed in such a way that this transistor has charge trapped. So threshold voltage high, this does not have any charge trapped. So this operates on normal threshold voltage. So it's low. Here that's what I've written. Low is normal threshold voltage, high is high threshold voltage. That means this high ones are the ones which are programmed in that row specifically. So now let's presume that word line goes high. When word line goes high, we know that word line would be equal to VDD. The high transistor has a high threshold voltage, so it does not turn on because it's programmed not to turn on. The low ones will turn on. And we know that when the high one does not turn on because of pull-up, they would have already pre-charged this to VDD, right? So this will say, this is D7, say this is D6, this is D5. So all this are zeros. So all of them were initially at logic high, correct? If this guy turns on, then only it will go to low, otherwise it will stay to high. That's exactly what I'm talking about. So D7 will stay to high. This is low, so the transistor, when WL equal to VDD, it's not programmed. This floating gate is not programmed for a higher threshold voltage. So this will turn on and it will pull D6 to 0, as I have said here. D5 high, so it will 1, D4 0. So this is how you program by using the floating gate and the charge stored on the poly gate. You ensure that your threshold voltage is greater than VDD, and this is how programming happens. Electrically programmable ROM. Now how does erasing happens in this electrically programmable ROM? Let's understand that quickly. Erase principle is based on the concept of ultraviolet light. Let's understand this. When you want to erase this ROM, in this case EPROM is what we are talking about, right? You have to expose this memory cells to ultraviolet light. Basically what you have to do is, you have to take this chip, expose it to ultraviolet light through a glass window which is present at the top of the chip. So there is an IC or there is this chip on top of it there is a glass window. So you have to take out this chip through the glass window, expose it to ultraviolet light. The ultraviolet light which is present, right, will increase the conductivity of the silicon dioxide surrounding the floating gate. So once the conductivity of the silicon dioxide surrounding the floating gate is increased, it will allow all the charge that was trapped onto the floating gate to be released, and now you can turn on your transistor. There is no charge on the floating gate, so it behaves like a normal transistor, and you can turn on your transistor with a normal threshold voltage. So basically what we saw is, we have to remove the entire chip, we have to expose it to UV light through the glass window which is present at the top of it, and when that happens, the UV light will increase the conductivity of the silicon dioxide surrounding the floating gate, which will lead to the floating gate losing its charge which it had trapped. Now what is the catch here? What is the drawback? Technically this process will take up to some time, less than an hour. Now the catch here is, when you remove the chip and expose it to ultraviolet light to erase, you have to erase the entire part of the chip, and you cannot erase a part of the chip or a part of the program. So when you erase, the entire memory has to be erased, and then again you have to reprogram the entire memory, which is ideally not a good idea. So in order to do erasing particular part of the memory and not doing it through ultraviolet light but through electrical phenomena, we go to the next type of memory, which is EEPROM, or electrically erasable programmable read-only memory. So let's quickly go ahead and see that. So the next one is EEPROM, electrically erasable programmable read-only memory. This will operate on a phenomena called as fallen northern tunneling. Again, it will be having a floating gate but with a slight variation. In the hot electron effect or the channel hot electron injection, we saw that this was the floating gate, right? And we also saw that this floating gate, due to hot electron effect, will trap the charge, which will increase our threshold voltage greater than VDD. Now, what change do we do in fallen northern tunneling is, or tunneling oxide MOS is, see my polygate shape changing. Initially, my polygate was like this, I beg your pardon, over the drain and the source. Now, towards the drain side, what change I'm making is, I'm reducing the TOX. If you see here the TOX was this much at the drain side. Here it would be a channel, right? If it's formed. So here it was this way. Here I have reduced the thickness oxide drastically near the drain side. Now let's see what happens. Again, in the basic clips, you have understand that if we have a very thin oxide and if we have a high gate voltage, then gate tunneling will take place because of E vertical, electric field of the vertical side, which is given by VGS by TOX. So we are going to use this phenomena to understand the programming of EEPROM, or will understand fallen northern tunneling and then extend it to understanding EEPROM. So now let's say case 1 is, we apply a positive voltage at the gate. When I apply a very high value, something around 20 volts at the gate, because this oxide is so thin near the drain side, right? And we know that gate tunneling can happen. The electrons will move, will get attracted towards the gate and will get trapped in the oxide. So the difference is, you don't need to do hot electron here. What you need to do is keep this node floating, keep the drain grounded. Now drain is grounded, gate is at a positive value. When gate is as a positive value, small value nearly equal to 0 or technically equal to 0 only. When gate is at a very high value, what happens is because of gate tunneling, the carriers will tunnel through the oxide because of oxide thickness is reduced drastically, so it becomes easier for the electrons or the carriers to tunnel and they will get trapped on the floating gate. And we know that when it gets trapped, again we can go ahead and increase my threshold voltage to be greater than VDD, and now we know, right, it does not turn on even if VDD is applied. So case 1, programming, we follow a phenomena of gate tunneling in which the gate voltage is put to a very high value and the drain voltage is 0, so the electrons will tunnel. Now this process takes place because of the tunneling oxide. When there is such a thin oxide, we can also call this as a tunneling oxide MOS, and this tunneling is so small that electrons move faster towards the floating gate and hence the tunneling oxide process is fast. Now case 2, when you want to erase, see this is electrically programmable, right? How did we program? By putting a higher value at the gate, say around 20-25 volts, and a lower value at the drain. So electrically we could program it. Now let's see how we can electrically erase it. To erase this memory, what you need to do is exactly opposite phenomena to what you did for programming. So what you're going to do is make your gate voltage 0, put a very high drain voltage. Now what's going to happen is the electrons which were trapped here now would be, because of the electric field, be attracted towards the drain side, or for that matter would be attracted. See, the tunneling oxide is very thin, right? And now there is a high voltage here, so electrons will get attracted towards a positive terminal, and in this process they will come back to your semiconductor, and in this way whatever charge was present initially because of programming, you can easily erase that charge. So this is nothing but electrically erasable programmable read-only memory. For erase and programming, you are just playing around with the gate and drain voltage. For erasing, we just saw that put a high drain voltage, put a low gate voltage nearly equal to 0. For programming, put a very high gate voltage, put a drain voltage nearly equal to 0. Now let's see the structure of double EPROM. So here there will be a change. We had been seeing that in ROM arrays and in EPROM we use only one transistor, correct? This is shown this way, but we drew it this way, one and the same thing. In floating gate we had this symbol, correct? But we had only one transistor in each row. Suppose this was my word line, this was my D7, this was my D6, this was either ground or it was connected to something else. Technically it has to be ground, not to something else. So basically what we are trying to understand here is we had only one transistor in my NOR based ROM arrays or my EPROM in that particular cell. If you have still got confused, very simple. Suppose it's a cell of an array. All the cells, each location would have had only one transistor, correct? Only one. Here, in case of double EPROM, you will have two transistors. Let's understand why. First, let's understand the two transistors. This is my floating gate transistor, correct? We have shown it with the input as word line. It's connected in series to a transistor which is called a select transistor, which will quickly understand what is the use of this. And this is my bit line. Just focus on this and now we'll understand in an array or in an array of multiple cells, how do you read and write? See, why are we trying to do this? We understood that the drawback of EPROM was that it cannot erase a specific part of the memory. To erase a specific part of the memory and to do it electrically, we brought a new memory which is double EPROM, electrically erasable programmable read-only memory. We saw how we can electrically erase. Now we are trying to see that how we can electrically erase only a specific part of the memory. So that's where we are trying to understand the structure. So I have just replicated this block 4 times and I have shown an array. Don't get confused. The diagram is simple. One transistor connected in series with other. This is a floating transistor. This is grounded. This is word line and this is word line dash. It's not complementary to this. It's just word line dash. Remember that. Here 4 different locations. First location, second location, third location and fourth location. In the first location 2 transistors, second location 2, third location 2 and fourth location 2. Fair enough? So I have shown this. As I said, N1, N5, N3, N7 are all select transistors. Okay. We have also seen for arrays what is the process of programming, what is the process of giving the voltages. For programming also, what is the process of giving the voltages. And we saw that unlike one transistor, each cell has 2 transistors. So this is the connection. This is a column, right? So all this will be connected to bit. Again, this is a column. So all this will be connected to bit. This is a row. So both the floating gates will get the same word line, both the floating gates will get the same word line, both the select transistor will get word line dash, word line 1 dash, both the select transistor will get word line 2 dash. So this is a row, this is a column, and the connections have been made to make a cell or an array. Now we want to erase a specific location. Say I want to erase whatever is present on N2, I want to do that. So for that, we know that for erasing, make the drain voltage high and gate voltage 0. Suppose the select transistor wouldn't have been there. There are a lot of transistors in this column, right? This is exactly the concept which is used in flash, which we'll come to very shortly. What would have happened is, this is all floating gates, right? This is all grounded. Basically, I'm trying to tell you why we are looking for this transistor. Suppose only this would have been present. That's what I've drawn here. So now I wanted to erase. So suppose I wanted to erase, I know that I have to make my drain voltage very high. This bit, this is nothing but drain. So I would have made this 25 volts and gate voltage has to be 0. So all of this would be technically not on, right, at the same time. And that means this will lead to a global erase. Means drain would have been 25. So all the column transistors would have gone drain voltage as 25 volts. Whereas the gate voltages were 0, so the erasing would have happened for all in that column, and that is nothing but a global erase. How does this select transistor avoid this? Let's understand this. So we want to erase N2, right? So for that, the first thing which we will do is, you will make your drain high, which I have done. This is drain for this, 25 volts. In that case, both these drains were directly connected to the floating gate, so both were getting erased, or all the transistors in this column were getting erased. Let's see how this is different. So this makes drain high, V bit 1 is equal to 25 volts. V bit 2 at that point of time is kept floating, remember that. So here N2 and N4 are in contention, right? Because this is 25 volts, this is floating. So no change on the drain voltage here. It's not 0, it's not 25. So it's floating. So this cell or this column is out of the picture. Only this, so this column is in contention, and specifically N2 and N4. So then we make word line prime equal to VDD. Fine. Now, because we want to erase N2, we'll make word line prime 1 equal to VDD. That means word line prime 2 is equal to 0. If this is 0, this select transistor N3 is off. N7 is also off, but we are not considering this column because we already saw that this is off because bit 2 is floating, correct? So this is off. N1 is on because word line 1 prime is high or VDD. This is on. This is VDD. This is a pass transistor. So drain voltage gets 25 volts, gate voltage is 0, correct? Word line 1 is 0, word line prime is on, so select transistor is on. So gate voltage, word line 1 is 0, so the gate voltage of the floating gate is 0, drain voltage is 25, that's exactly what we want, so erasing will happen of N2. Similarly, we can show it for programming also. Remember that all other bit lines have to be floating, so that nothing happens in the other columns, no erase, no programming, if you want to do a specific thing at a specific location. So this is the concept of double EPROM. Flash is also a type of EPROM. The difference is a single transistor. They don't have a select transistor. I've just explained you this, word line 1, word line 2, so on and so forth. So if I have to erase, if I give 25 volts, this is drain, right? If I give 25 volts at the drain, then all these transistors, because the word lines would be 0, would be erased at the same time. It's nothing but a global erase. In the next clip, we will see NOR based flash memories and NAND based flash memories. I hope you have followed this. Stay tuned, take care, and thank you very much.